I got a new cell phone, and here's what they told me. They said that it was going to be $39.99 for the first 200 minutes and 10 cents per minute after the first 200 minutes. So I thought, can I make some kind of function to describe my cell phone plan? And so here I have it. I have it right here using Graphmatica. I have $39.99 for the first 200 minutes. Can you see that?
I do.
And then I have, after that, it is 10 cents a minute. So I have really this one function, and then this, it's like a whole other function here.
So it's like two pieces.
It is like two pieces of a function. It's really, you can't really easily describe it with one function, but with two linear functions, you can see that this is nicely described. And I think I have another example. So here's another example of a function that really can't be described with just one equation. Here I looked up the shipping charge for different weights, and a particular company charges $1 per pound for anything from 1 to 10 pounds.
And
$1 per pound.
Why don't you draw over that?
I'm going to draw over that because I don't know how well that's going to, okay, it's a little spastic, but there we go. So this represents $1 per pound for the first 10 pounds. Then 75 cents for anything that weighs between 10 and 20 pounds. So a 10-pound item is all of a sudden a little bit cheaper. It's a little bit strange, I know, at this point. It's a totally different function. There is a cost of items between 10 and 20 pounds. And finally, 60 cents for anything greater, 60 cents per pound for anything greater than 20 pounds. So here I have another piece of a function to describe that. This continues forever, of course. So here's another example of a real-life function that really can only be described using pieces of a function.
So Mr. Haas just gave us some excellent real-life examples of these things, these functions that we can describe in pieces. And strangely enough, these functions have a name, and they're called piecewise functions. Piece, as in coming in pieces, wise, functions.
As in they're very smart functions? Is that?
Something like that. So, how can we graph these? Here's an example of how we're going to actually be graphing these things. The notation seems a little funny at first, but actually it's just saying this is one function. So even though the function is in two different pieces, I'm referring to it as one function. That makes sense. So we have one function, which we're calling f of x, and we're saying that's equal to 1/3 x plus 2 as long as my x's are less than 0. As soon as I hit 0, I jump to this part, this piece of the function, which is described by the equation x plus 2. So let's see how this is going to work. All right. So down here, where my x's are negative, I'm going to be following this line. If you want, we can just plug in x's, right? Or we can use our knowledge of how to graph functions. That's a linear function. So I'm just going to graph that knowing that this is my y-intercept and this is my slope. Is this all right? So my y-intercept is 2 and my slope is 1/3. So I could go up 1 and over 3, up 1 and over 3, but I'm just wanting this part of the piece to be where x is less than 0. So I'm going to go down 1 over 3, down 1 over 3, and there's my line. Now notice I stopped right where x is 0. That's because I'm following this piece only for x values that are less than 0. When x equals 0, boink, I jump to this piece. So in fact, I'm going to do an open circle there. And now I am on this piece. X plus 2. I'm just going to graph it the way I know how to graph lines. My y-intercept is 2, 1, 2. Oh, isn't that handy? It ends right where the other one picks up. How neat. And my slope is 1. Up 1 over 1, up 1 over 1. So there we go. So this looks like Mr. Haas's first example with a cell phone. Vroom is the first piece. It connects the second piece. But you can see that there are two distinct pieces. The slopes are quite different. So I just graphed a piecewise function.
So let's graph one more piecewise function. Here it is, and as Ms. Stewart said, it's really just some function divided up into two pieces, two or more pieces actually. The first piece, it's a linear function also. It doesn't always have to be linear, but this one is linear, and it's for all x values less than -1. So this is going to be a little bit funny. I'm going to graph it as if it's a regular line. I'll start at -3, that's my y-intercept, 1, 2, 3, and the slope is -1, so I'm kind of working backwards here. Like that, it looks something like that, but I'm only supposed to go up to x values -1. So I'm just going to start it right there at -1. I'm going to work backwards, so that's the first piece of the function. The second piece of the function, 3x plus 1 for x values greater than or equal to -1. So I'm starting at +1, and it's slope of 3, up 3 over 1, down 3 over 1. Hey!
Hey!
Lo and behold. So what do you think, Stuart? Do the two pieces of the function always have to connect to each other like that?
I don't think so. Didn't you show us one example
Oh, that's
when
right.
they weren't
I think I did.
connected?
So perhaps let's try another one.
Let's do.
Okay, so let's try another piecewise function. As you see, this is broken up into 3 pieces. So let's just start here. This says for all x values less than -2, my y, my output is going to be 4. All right, so let's see, -2, 1, 2, 3, 4, but it doesn't really equal it there. I'm going to put an open circle. So for everything less than -2, my y value is going to equal 4. So far, so good? All right, so there I'm happy. I get to where x is -2, and so I bounce to this next piece. This says for all x values, for all inputs between -2 and 2, so that's -2 to 2, my output, or my y, is going to be 2. So there's a y value of 2. And let's see, that's a closed circle because it's or equal. And right when I get to my x value of 2, I say, oh, I'm done with this piece, let's go to this piece. For all x values greater than 2, my output is going to be -1. So let's see, 2 is the transition, so I'm going to put an open circle at where x is 2, and my y value is -1, and there we go. So look, this is an example of a piecewise function where the pieces don't touch. They don't touch. But every single x value is defined. In other words, every single x is in the domain of this function. Any